Blah, 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 blah. Blah, 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 blah. Okay. Cool, man. Just getting some prints. Just getting some prints. Don't even worry about it. Don't even worry about it. Word. Be right back. Don't mind me if I'm limping. What's up? Yeah, I left as you joined. What the hell is my problem? Unbelievable. I can't believe I would do such a thing. This is not working. Is this like, what are the settings here? I think that this is too... I'm not using the right config here, man. I don't know if I saved this. This should be colder, though. What's up? You good? You good mentally, physically, or premature deathly? I obliterated my knee last night in a parkour session. Bad, stupid landing. So so I can't straighten my leg. So no push-ups today, but dips are on the market. So keep that in mind. None. Okay. Nope. Stop. We gotta restart this. Yeah, I should have said hi first. Yeah, come on, man. You just said he left as I joined. What the hell? Alright, be right back. Oh, fuck me. Prints are not looking good. Gotta go a little slower and a little colder. Oh. But I think there. Okay. We'll try that. Yeah, we'll try it. We will try it. And we will export this config so we don't forget. I'm going to call it int config for real this time. Cool, man. Bat motor cap.g code. Let's go. Hit it. Sorry. Hello, everybody. Welcome. Yes, I would like to override it. Welcome to my stream. Oh, my knee hurts, but the doc said that my critical knee components are fine, thankfully. So I'm just going to be swollen and limping for a couple days. No problem. I am, of course, indestructible. That is something that I don't say to my girlfriend because she will immediately dispute it. But that's what we're going to go with today. Cool. So that's Charlotte. You guys know her. You guys love her. Just, tinkering with a couple things over there. Get yours now. But we're going to go back to the web because the web is like coming to a place where it's like going to be done soon, like the design. So excuse me. Jesus. It's still smoky outside. I can only see about 2-3 blocks in the distance. Thank you, Canada, and thank you, billionaires. So we are going to work on this. You can see the pressure vessel shape is coming into view. I have the valve placed here. I've made it shorter than the old valve. Where's the old valve? Right up here. That's the old valve. That's the new valve. So shorter because we don't want things sticking out as much in this design. And it doesn't have to stick out as much, I hope. We'll see. We will see. I still don't have the mounting. That's part of the reason why I had to stick out so far on the old design, because there was mounting. But yeah, pressure vessel, kind of a crazy shape. So we're going to have to deal with that if we can. So what is going on here? That's one part, right? Okay. Cool. That's what I thought. I need to figure out exactly what kind of mechanism I can get away with here, because I'm starting to think of different things other than the 2 levers that I had before. And I'm kind of like, should I be doing that or shouldn't I be doing that? Because a lot of thought went into that initially. So what I want to do is actually watch the video where I created this. It's kind of like reading your own paper, I guess, to try to remember what I did and why I did what I did. Go here. All the way back. This video. Oh, you guys can't hear it. We're gonna fix that. Don't you worry. I've got to watch this, otherwise it won't be possible. Sound. Hello. Okay, good.
Redeem your points today.
Great.
The Labrador Retriever and the Golden Retriever look similar, but eat and process energy differently. That's why Royal Canin developed over 60 formulas.
How did I start?
Snoring. Bumper cars. Oh. Oh.
Be right back.
I have to do better.
Struggling how to end that commercial balls of steel.
We already did the brick, and then
Yeah.
you did the hammer. Cut to black!
Yeah, cut to black. That's an excellent idea.
Yeah. Boom!
So I came up with this random way to talk about this rather interesting comment that I got right here. And I'm not going to put the person's name. They also gave me some really helpful advice with the machining, which is so much appreciated. Thank you so much. I just want to, sort of open the discussion a little bit, whether you use guns or you don't use guns, or you like guns or you hate guns. It's just really not a matter of fact. Newton's fourth law of motion is not that guns are the best way to protect yourself. Maybe just think about what the future could look like. But then we also have to think about the different kinds of defense. What kind of situations will people be in where they need to defend themselves? If it's home defense, firearms may be the best way to do that. There are a lot of people who carry things like mace or pepper spray, intentionally non-lethal methods of self-defense. And like this person said, the device does not really need to exhibit a capacity for murder to be able to be an effective deterrent. When they're having a night out or they live in a bad neighborhood and have to walk home. Ladies, you know what I'm talking about. Men, talk to your girlfriends. You're having a night out. You could encounter people who are dangerous and they might not be armed. And mace and pepper spray is a very effective deterrent for these people. A lot of the crimes that are executed against women where mace or pepper spray might come in handy, these crimes are more likely to be executed by people they know as opposed to
too expensive.
Strangers. I think this is a valid criticism. And I'm not going to tell you that this thing that I painstakingly manufactured with my crappy machine is going to change the world. What we're trying to create here is something that is sleek. I know it's not yet, but it will be. Real ejection device. This is your company, and this is your...
All right.
It's a super just advantage of 10...
We need to get to the science part. Sorry, guys.
Real money. So the first thing I want to work on in this video is having something where this device here, and then you've got these two parts that are on a pivot point. So when you want to put this on, I want you to imagine you're just, full bracelet. You're just going at it just like this. And then let's say there are some springs that bring these back around. Then when you want to take it off, there's some button that undoes this latch.
This was cool, but it doesn't really work when you have to fit stuff around the whole bracelet. Okay. What are we doing here? What is this?
That allows them to still, interact somewhat strongly.
Hi,
even
Jules.
though what they want to do is
We got
bring
Jules.
this center to that center. I also realized, because I'm an avid watcher of many 3D print designers on Instagram, that I could actually easily embed these magnets inside the 3D print by placing them into the 3D print in the middle of printing. And that's a technique that I did not come up with, but it is super handy. So there's just a magnet inside there and a magnet inside there, and you can see they stick together. And there's no fasteners needed, no glue needed. This is the magnetic spring. I also added sort of a stop. This can only rotate 90 degrees. And I also added a little latch mechanism. So you can see here, there's a little leaf spring here.
This didn't work, by the way.
The leaf spring looks like this on the inside. And it's super easy assembly. All I have to do is stick it overall. The only issue is this kind of leaves minimal room for everything else in the wristband. The part of this clasp mock-up that doesn't move is actually mostly taken up by the pressure vessel itself. But the thing is, this is definitely the clasp mechanism that I want to go with. So we're going to have some creative solutions to figure out where to put everything else that goes into this device. To start, I want to focus on the valve actuation. There's a bunch of different mechanisms that I've created for valve actuation in the past. Levers, screws, gears, pulleys, capstans, all sorts of things. I really want to try to streamline it, come up with something that's compact or at least fits, sort of within this C shape, and something that is optimized from an engineering standpoint in the sense of, what is the minimal transmission that we need such that our actuator can open this valve. It takes quite a lot of force to open this valve. I don't know exactly how much, but the first step in figuring out what kind of transmission we need is to actually measure that amount of force. All right, so I've mounted my pressure vessel to the table here. The liquid will be at the bottom of this pressure vessel because of gravity, and that means that I can see when a stream is coming out, because if it was vapor, it would be invisible. And then I have this sort of like a marionette controller. I have no idea what that's called. I've built it such that it's just a single rope winding through this entire thing, so that the tension is the same, and this mounts right here. And I've got this thing attached to this spring force gauge, and I can pull on that. Sorry, it's not very sophisticated. I intend to just take like slow motion video from directly below and sort of just watch what the reading on the force gauge is at the instant the valve is opened. I've been doing a great job so far with my the.amazing. Just one donations via PayPal. All you have to do. Now, while I originally planned to view this video and try to discern the force from it manually, I actually realized I could use some computer vision techniques. So I ended up isolating the stream of fluid, doing some segmentation, then doing some thresholding. And that actually gave me a pretty accurate numerical value for whether or not the valve is open. Then I could do some motion tracking on the force gauge, and registering that to real-world measurements, I was able to get a value for the force from the video. And so I could overlap these two graphs and then only sample the force readings above a certain valve opening threshold. That gave me an average force of opening the valve of about 20 newtons and a maximum force of about 28 newtons. This contrasts with another analysis I did, that is the force based on the vapor pressure and the diameter of the outlet, and
quite
that
a different
only predicted
result.
about 5.6 newtons.
Yeah. So
there must be quite a lot of friction, or there must be some other force acting upon this valve when it tries to open. Of course, measuring the force that it takes to open the valve is only one side of the equation. To design a transmission, we need to also know how much torque this motor can exert. And I don't really have a number on that, so
this is the good
I decided to just measure it. So
I think this is the same motor that I'm still using. So
force values at various voltages for this motor. Here I've plotted these torque measurements as a function of the voltage they were measured at.
You didn't miss much, Shira. I'm just I'm rewatching this because I need to use it in my new valve actuation design, the analysis that I did here. I don't want to do it again. I just want to recall what I did over a year ago because it should be the same result. But I kind of want to see if I can get away with something that's not the levers here. Because I want to try to reduce the compliance, I guess. And when you have a really long lever, and I do want to make it out of plastic, I could machine everything, but that's like, it's just not feasible from a cost standpoint. So I want to see what I can get away with. And so maybe more, like less materials in bending would be nice. If I have to do the levers, I'll do the levers. I'll find a way to do it right. But it has to be the same kind of transmission with the same kind of gear ratio. So I'm just rewatching.
And it seems like it's a pretty linear relationship.
What I have.
That means we can fit a good old y equals mx plus b to these points. Since we got this data of how much force it takes to open the valve and how much force the motor can exert, we need to talk about how we can use that information to design this transmission. So the thing is, transmissions are all about an equivalency of power. So power in has to equal power out. Now that's assuming efficiency is 100%, and this essentially would only not be true if there's friction in this transmission, which of course there will be, but certain types of transmissions are closer to 100% efficiency than others. What is power in? It's equal to the torque multiplied by the speed. Now this speed is in radians per second, but we can turn it into rotations per second by multiplying it by 2 pi. Here we represent rotational speed as n rotations divided by t time. On the valve side, we have this valve that has to move a certain distance, x. And the force that's exerted as it moves this distance is F. That's what we measured. Now we're going to assume this force is constant as the valve moves, and that means the work that is done, which I'll represent as W, is equal to F times X. So if we want to get the power that's transmitted to the valve, we simply have to divide work by time. Now, the key equivalency between these two is that the amount of time it takes the motor to spin to open the valve is the same amount of time it takes the valve to open. First, let's start by setting power in equal to power out. Torque N2 pi over T equals Fx over T. Since these times are the same, we have Fx equals T N2 pi. Now, we have this torque as a function of voltage. That's the data that we gathered for the motor. And if we rearrange this, we can have the number of rotations that are required to open the valve as a function of voltage as well. Now, this is actually a lower bound. Essentially, what this is telling you is that it's not physically possible to open this valve with any number of rotations less than this amount. So this.
Okay, great. Let's keep that in mind. So the number of rotations is key here, right? Because in this original version, I only have the motor rotating halfway around, and that's great because then I get like the maximum, I get a lot of speed out of that, right? Because it doesn't take very much time for the motor to rotate halfway around. If I had the motor, like if I wanted the motor to have to do like 5 rotations to open the valve, which according to this law that I've discovered is still possible, it would take more time, and that's not as nice for like a very quick release mechanism. This is good info. Okay.
With any number of rotations less than this amount. So this becomes our lower bound for what is possible. But then there's a question of what is this torque exactly? A key characteristic graph of a motor looks something like this. So if this is torque and this is speed, this is called the stall torque. And that's what we measured. It's the torque when speed is 0. This is called the no-load speed. And that is because it's the speed when the torque is 0. Now, what about the effect of different voltages? Because we measured this stall torque at several voltages. Let's say this is the graph when voltage equals 1. What happens if we increase the voltage to, let's say, 2, is just it shifts the curve upward like this. So you can see we do have that increase in stall torque that we observed from our graph. And our data for stall torque, depending on voltage, had a very linear relationship with an intercept at 0. And we fit a best line to it. And this relationship actually is theoretically expected. And the reason for that is because you can model any DC motor as a voltage applied across an armature that has some inductance and some resistance, and being applied across another voltage where the voltage across this is equal to the motor constant K times the speed, and this is called back EMF. Now, when we're at stall torque, the speed is 0. This inductor, which usually has the equation voltage across the inductor is equal to the change in current, but because we're at steady state, current isn't changing. The voltage across this goes to 0. We're just left with a simple voltage V across a resistor R, and that exhibits the current I equals V over R. That's Ohm's law. So that's a linear relationship between voltage and current. Now I want to be clear here that this current is the stall current, IS. And because torque is always proportional to current with this same constant K, the stall torque is proportional to voltage over resistance. The slope of this line is K over R. Hi, it's me editing here, and I just wanted to say I did measure the resistance of the motor, and it's about 7.5 ohms, which means we can actually calculate the motor constant without ever measuring current, and we get a motor constant of about 0.05. So it's kind of cool we got all that just by, taking a few measurements, but we don't want to run this transmission at the stall torque, right? Stall torque means the motor isn't moving. So we do need it to move. Now recall that the power that a motor transmits, as we talked about just briefly before, is equal to the torque multiplied by the speed. When you define your operating point on this curve, power is actually the area of the rectangle that's formed between the origin and that operating point. So we actually get the maximum power transmission at the stall torque divided by 2. Now we can change sort of the ratio S. So right now we're talking about S equals 0.5. If you move S closer to 0.3, you have a little bit better efficiency, but... yeah, S basically being the percentage of torque that you want to transmit with respect to the stall torque of the motor at any given voltage. So that's why this line here is still a function of voltage, but it's S times the stall torque for S equals 0.5. So it's a line that's halfway down from the original line that we measured. If you move S closer to 0.3, you have a little bit better efficiency, but we're going to be working on maximum power transmission. Now recall that this is an upper bound, meaning that any point in the upper green area will actually still function. It's just that anything below the green area is physically impossible. Now, when I first saw this curve, I thought, wow, these rotations actually look quite low. If we're operating at like 2.4 volts, we only have to do half a rotation? That seems crazy, and that's not been... Is that true? Is that what the graph says? That's why I came up with half a rotation, of course, but I just saw the graph and it did look kind of odd to me. That's not half a rotation. That's one rotation. Did I get that right? Below the green area is physically impossible. Now, when I first saw this curve, I thought, wow, these rotations actually look quite low. If we're operating at like 2.4 volts, we only have to do half a rotation? That seems crazy, and that's... Okay, something's up here. If I go to my original Desmos graph, let's see. That's why you always check your work, people. Oh, brother. Bruh. Don't do me like that. Come on. Okay, let's try to find this. Da-da-da-da-dum. A lot of Charlotte legs going on here. I can't find it. Let me see here. Well, what if I just No, it's got to be here somewhere, right? This one. Yeah, valve transmission. Okay. Let's see. So that's this graph here. Okay, got to try to change the scale. There we go. 0.5 rotations. I literally have it marked right here. 2.48 volts, 0.5 rotations. What is up, 610? Welcome. So this graph shows it, and I have it right here. Fx over 2 pi s torque. Fx over 2 pi s torque. That's right. Okay. So I think the plot that I showed in the video is wrong, but it's like this one right here. I think, is this with s equals 1? No. Maybe it's got to be. Wait, S.5, that's what I'm saying. I think that tonight I might actually make and solve the equation so I can make a graph to find structural combinations that make a working web fluid. Huh? Okay. Might make and solve the equation. Cool. Love that. Always solve equations. So I can make a graph to find structural combinations to make a working web fluid. That's really interesting. I would be interested to see how that comes up because I feel like that's something that could only be done empirically. I've always felt that. And that's why I'm always pissed at Blood Spider for not writing shit down when he does his, he was doing his, just throw a little bit of this, a little bit of that and see what happens. Well, I feel like this works well. He never did any like actual tests. I was like, you could be such an asset, But he was just like, just do it. He's not a scientist, It's how I'm trained. FX. Okay, so that's that's what I think, and this looks more like it's higher or farther. So we've got like a 2, 1 combo. And here we've got, yeah. So, oh, sorry. There we go. Actually, I'm really happy that this graph still exists because I could use it right now. The blood casts have become stagnant. That's too bad. Yeah, I was supposed to be on one. I think that I was popping off because of critical and everything, but then that kind of died down, and Blood Spider was like, "Meh, he's not actually that cool." So S is it's like maybe 0.2, 0.3. Maybe this is where that comes from. This looks to right up there. Let me try to get the scale similar here because I think this is where that comes from. So I showed the wrong graph. This is the graph for S equals 0.3, which I guess is still true because I don't say what S is in this graph. But remember I was talking about how 0.3, S equals 0.3 gives you a little bit more efficiency. So maybe that's what I was going with before. But I don't want more efficiency. I want more power transmission. There is a difference. And so I go for 0.5, which is supposedly the most power transmission. Like I showed the area under the curve here, right? Yeah, the area under this curve is the maximum at half the stall torque. So that's what I was going to go for, maximum power transmission, not maximum efficiency. Efficiency in this case isn't really a big deal because it's not running continuously anyway. It's just a short burst of energy. So yeah, so that's interesting. So I said 0.3, and it does look like it's 0.3. Very interesting. Where is my Desmos? There it is. So yeah, let's get that scale looking similar. I also want to show just to kind of I want to see the inequality as well. Okay. Please be green. Please be green. Okay. Right. So for what this is telling me is that at s equals 0.3, for half a rotation to open the valve, I would have to use, dude, seriously? If you, I have 3 degrees in mechanical engineering. Of course, I know how to use MATLAB. So MATLAB, of course, is very expensive, and I'm no longer a student. So there's that. Octave, yeah, that could definitely be used. But Desmos instantly comes with a GUI. If I'm doing something that requires more complexity, like control analysis or optimization, of course you can't use Desmos. But my choice would actually be Python at this point. Just because it's also great because you have libraries for literally everything. But yeah, could use Octave. Octave is just like MATLAB, but a free version if for people who don't know. But yeah, I know how to use all these tools. I'm choosing Desmos because the guided user interface is immediate. So you don't need to program that in. It just helps me a lot to manipulate graphs visually. Yeah, it's a great tool. And I'm not the only engineer who thinks so. Well, what was I doing? I wanted to see, I think this looks like the same graph. So clearly when I plotted this, I was using s equals 0.3. So this goes 0.5. That's what I ended up using, which is where I got the figure of, what is the purple graph from? Purple graph. Oh, that's like diameter. Minimum diameter. That's right. Or input diameter or something like that. Yeah, we'll get to that. Okay, so it's clear that I said that you can use this graph to figure out the minimum number of rotations that are able to open this valve, no matter what your transmission is, for whatever supply voltage you have. So my supply voltage is here, right? So I'm not actually operating with that high of a safety factor. In this case, if I want to operate, well, there's of course also the safety factor of we're not operating at the stall torque. So like our true safety factor is, how can I plot draw this right here? I'm going to do SF equals, it's going to be S, well, 1 over S times, I'll just call this VS. This is our supply voltage. But of course, our minimum supply voltage, like how low this battery could get, probably, let's just go for 3. I don't know. Maybe we'll just keep it at 3.7, just to not complicate things. VS divided by V, I have this named, right? V min, yeah. VS over V min. 1 over S, wait. S times V min over VS. That's right. So our real safety factor ideally is 3, which is not bad. But in practice, I think there's a lot of things with the mechanism, like the fact that I'm using this really long lever to get mechanical advantage, but it's kind of like compliant, you know, and twists and turns, and that's been really annoying. So a different type of mechanism might be warranted. But it's good to know that theoretically, we could still be operating with a safety factor of 3. And that's 3 with respect to stall torque, though, not with respect to maximum power transmission. I don't know how to judge that properly, but, you know, 3 is not a terrible safety factor. All right, let's keep going with the video and see what I say, because this all looks good so far.
Anything below the green area is physically impossible. Now, when I first saw this curve,
there's bending
I thought,
stress
wow, these
most of all, I
rotations
think.
actually look quite low. If we're operating at like 2.4 volts, we only have to do half a rotation. That seems crazy, and that's not been my experience in the past. But you have to remember that this is just what's physically possible according to physics. We can also examine this based on engineering. So if we have to pull the valve backwards a distance of x, we can imagine using a string attached to a winch. Now this winch has a diameter, which I'll call d in. We need to rotate this only 0.5. So that means that x, the amount that this is pulled, is equal to the circumference d in times pi multiplied by the number of times it's rotated. d in is equal to x divided by pi n. Now, if we plug in some numbers here, x is actually quite small, 0.00088 meters. This is defined by the design of the valve. It's going to be something like 0.0006 meters.
You're not impressing my stream. Everyone knows you're using a calc. Calc is calculator for short, chat. So, what? Okay.
0.6 millimeters.
All right, this is still one of my favorite jokes. It's really funny. I haven't put that in a video in a while. Okay, so what I'm saying here is that this is the valve. It is pulled a distance x by a winch of diameter d in, half a rotation. So the distance x equals d in times pi times n. That's just geometry. And then this, I guess I'm just giving examples here. Or, oh, wait, maybe I said something important. Hold on.
By the number of times it's rotated. d in is equal to x divided by pi n. Now, if we plug in some numbers here, x is actually quite small, 0.00088 meters.
Wait. That's interesting. Did I explain where I came up with that? Because I'm kind of trying to remember. And I think I looked at the valve and was like, if it opens 8.880 microns, right? Let's look at the geometry here, because this is the same geometry that I had before. Unless I did change it, but I think it's the same. Same valve geometry. Okay. So I said if this is sealed, 0.88. I guess we'll bring that along. I mean, yeah, you do open the valve then, but I think maybe the problem comes because if I am only expecting to compress this valve 0.88 millimeters, that can easily be compensated for by bending of 3D printed material. You know, 8.8 millimeters is nothing. So maybe I should plan for a longer stroke. You know? Well, let me look. What did I actually do in Medesmos? X. Here, I put that in. So that comes into play for all of these equations. And that's really interesting. If I amplify that, I'm guessing things will change quite a bit. Okay, let's see. Because what I want to do to get, you know,
Maybe maximum flow would be nice. 2 millimeters. How about that? That looks really nice. That's like the maximum that I can get without these wall ceiling O-rings kind of getting into precarious positions with respect to the wall. So 2 millimeters would be real nice. It's really interesting that I said 0.088. 0.88 millimeters. It's really interesting. I know I measured that from something, somehow. All right, who's ready? Boom. Okay. So now we're getting into something a little bit different. Now our safety factor has dropped to 1.3 from 3. So that's a lot more precarious. And it tells us that we should be using a supply voltage of 5.4 volts instead of what we have here, which is our supply voltage of 3.7. Just want to change the style. How about that? So that's our actual supply voltage. So bad. So if we increase our N desired, maybe 1 rotation will suffice, which means we can't use the same type of transmission. And then our safety factor is 2.64. Really interesting stuff. Yeah. Okay, so my working theory right now is change the theoretical model to have a longer valve stroke. Yeah, because that also plays right into the mechanical inefficiencies in the valve design, the bending of the components that should be rigid. That kind of, 2 millimeters of bending is a lot harder to do than 0.8 millimeters of bending.
This is defined by the design of the valve. It's going to be something like 0.0006 meters.
You're not impressing my stream. Everyone knows you're...
Stop.
Yeah, so that's not happening. And also, I don't want to do cable-driven mechanisms anyway, because they're really difficult to assemble. And the motor shaft is actually 3 millimeters in diameter.
So what I'm saying here is this is physically possible if you have a shaft of that winch to be 0.6 millimeters, which is not physically possible. So I am taking that into account here.
So we really can't get away with any D in less than 3 millimeters, and probably should be even more than 3 millimeters.
So this is why I'm doing a transmission, right? Because you can get a lot of torque theoretically from a motor if you just have a winch around a shaft that's extremely small, right? But physically that doesn't work because you can't have a shaft that's extremely small.
How do we solve this problem, this constraint on the input diameter? This is where a transmission would come in. We can rewrite our equation for D, again, as a function of voltage. This time we plug in our function for N as a function of voltage in the denominator. If we add a transmission, this equation for N is not going to change. So that means that everything in the denominator here remains the same. So if we want to increase the diameter of the input, we have to...
Remember, this equation up here doesn't change because it's about power equivalency, which is not affected by transmission.
To increase the input stroke. What we can do is add a transmission such that the input stroke X is actually equal to some gear ratio, we're not going to use gears, multiplied by the distance that the valve has to pull.
Yep.
Similarly, the force that goes into this transmission is equal to the force the valve needs to open divided by that ratio G.
Yeah.
How many turns do we want the motor to have to do to open the valve? So if we have number of turns greater than 1, now we're talking about we have to do things like gears or belts,
Yeah.
you know, like transmit.
We can't do like a simple lever transmission if the motor goes through a stroke that's greater than half, really.
Missions that can go greater than 360 degrees.
Yeah.
If we keep n less than 1, suddenly we're thinking about using things like cams, slots. And there's a specific
Cams for a one cams for a 360 degree rotation, I suppose. Yeah, of course. As long as there are end stops. But to be honest, I do know slots. What am I talking about? I do know that you can create like a spiral cam. I've done that before, and I thought I was a genius, but I scrapped it for the cable shooter project. Okay.
type of mechanism that I have my eye on, and that is where n is equal to 0.5, or a half turn. So I want you to imagine that your motor is driving a wheel, and this wheel is attached to some peg, and this peg is transmitting force to a lever, which has a pivot point here. And so as we get that half turn, the motor moves the peg this way. It ends up here at its farthest point, at its farthest point horizontally, and finally ends up here. This means, of course, that this peg needs to have a slot to accommodate that horizontal movement. As the motor moves through its half turn, this lever will end up rotating about this pivot point to a final position here.
This is what I ended up with.
Point on this lever to get different kinds of mechanical advantage. So let's say this lever gives us a mechanical advantage of L1. We have our valve moving back and forth. The question is, what kind of L1 is necessary to modulate this distance such that D in will rise above 3 millimeters for a reasonably low voltage? The amount of space we have to work with is just what's on this bracelet. Here we have our motor, and the motor has an axis here. So I want you to imagine this wheel that we drew here is right here, being driven by that motor. So when you look at it from the front, you'll see the circular shape, but on this side you just see that. And the valve that we have to actuate is down here. That motion is along this axis. So what we could do is we could have that lever essentially with a pivot point here, basically rotating like this, and that lever basically...
I'm still fascinated by the Lugri model of friction. Just only have so many hours in a day, you know? That's for the cable shooter project I'm mainly thinking about, but I haven't had the chance to do the experiments I want to do yet.
It takes up this whole space. A mechanical advantage is the ratio between this distance and this tiny distance here. So we can see by modulating our D of V model, by adding G and modulating X, suddenly we see at 2.4 volts, this transmission...
So that's where this comes into play, is the gear ratio of this transmission, which... Where the heck is my... What the heck? What button do I press for showing all the windows? Okay, there it is. All right. So the gear ratio comes into play. This purple graph that's all the way down here, different units. What is this yellow one? Oh, that comes into play for the purple one. Okay. That's the stall torque. So we're not going to worry about that or the data that we gathered. Okay. So
I don't know what this is. Is this the shaft? H? Height? Height. No, that's 30. H equals... Wait. No, D shaft. Yeah, that's D shaft. Okay. So that's the shaft diameter of the motor. And so if that gear ratio, which is, where is that? G. Oh, maybe I don't have it programmed in. L total, that's what I call it here. And just have L and L2. Where's L, bro? Oh, there. Okay. I'm gonna just gonna erase this and make it a slider. So right now it's 6. So if we go between 1, well, 0.1 and I don't know, 10, then step of 0.1. Okay, clearly that didn't make a difference. What is this graph? D in x1 over n rot v pi. Oh, wait. What am I seeing here? This is just, what is x1? x1 is a transmitted distance, right? Where is that? Here, yeah, L2. Okay, so here's the problem. This can change to L tot, which is our gear ratio. Okay, right, so at a gear ratio, I understood this correctly, I promise. I'm understanding my own work. Where did it go? L tot, right here. So right, at a 1 gear ratio, we get a shaft of 6, or a winch of 6, which is dumb, or 0.6, which doesn't make sense. If we can bring that up to, because maybe we'll use gears, right, somehow. Got to get this above. So before we had 6, which brought us to like a nice 3mm shaft. And that's the input shaft, the input wheel, so to speak. So if we use gears, this could be like a pitch diameter. Interesting. So we can modulate this now to deal with that. What is the yellow lines again? X1 and D in V min. Have you been working on other formulas too? 610, I think quantum entanglement might be sufficient. What? Quantum entanglement? Quantum entanglement is probably more than sufficient, I would assume. For whatever. Sometimes I don't know what you guys are talking about. Okay. So this, I guess, is the x1 versus dn. These are not the same. I don't even know why these are plotted the same. So they're just the same color for no reason. So this is that one there, but
we don't need to see that. So this is the distance that we need to pull, I guess. Right? It's strange. This changes the number. Right, so we want, well, 1 rotation now. How about that? 1 rotation. So if we do 1 rotation, then x1, which is the distance we have to pull, goes up to 10, which could be, that's a geared distance. So the valve will only pull open 2 millimeters, right? Because if we do y equals xv, that's 2 millimeters, and then the gear ratio determines the actual like input pull. Okay, great. Got it. So yeah, can make that less or more. But I'm a little bit like the input shaft is determined interesting. I think something
becomes
interesting
possible
is
from
going
an
to happen
engineering
there.
standpoint because D is suddenly above 3 millimeters. What I actually decided to do, this part is taken up by some lever that has a mechanical advantage, and this part is taken up by another lever. Our G actually becomes L1 times L2. When we add this G to modulate our D of V model, suddenly this becomes very feasible from an engineering standpoint. After tweaking the model a little bit, I got exact numbers that would work for L1 and L2, such that it would fit on this wristband and be able to actuate the valve theoretically at a very low voltage, possibly less than 3 volts. I don't expect it to be that low in real life. A very exciting prospect for me.
Okay. So I'm in an interesting situation here. Am I? Wait, I think the math is consistent. Hold on. Because the pull distance at the input that we're going to need, because this is all based on winch geometry, right? That's very simple geometry. So that's x1, and d in at v min is the diameter of the shaft that I'm going to need. And if we multiply that by pi, we get the pull. Okay, so the math is consistent. Right, thank God. Okay. So how do I translate the winch mechanism into something that I actually will like to use? Because I hate winches so much. I hate them. But it would work. I'm better at making mechanisms than I was when I made this video. So maybe I can take the old math and apply it to some new engineering. I could have a pulley shaft of 3 millimeters easy. That's no problem. It could rotate once around, and then this gear ratio would have to be Still 6. The alternative thing to do is to gear this down immediately. Okay, everything's coming back into picture for me. Nature calls. I'm going to be right back and think about this while I'm, whatever. What up? Oh, gosh. Okay. So, what the? Okay. So what's the dealio here? I think I also want to look at the opening time. But I think that that's right here. Is that this? N desired times 2 pi over omega 1. And omega 1 is this, which is, what is T1? STM of 3.7. Make this VS. So changing the voltage won't change the torque. It'll change the torque when stalled, but other than that, the torque only depends on the physical characteristics of the mechanism. Like how much force the valve takes to open. So the torque when applying this is an approximation of the speed, right? It's going to be the torque around the operating point. The torque at the supply voltage at our operating point, which is S equals 0.5. We can get the speed which is a function of voltage and torque. So supposedly our opening speed here is 0.1 seconds. Probably going to be less. Like, let's be real. But it's not bad. What happens if we increase our gear ratio? Does anything happen to that? I don't think so, which seems kind of wrong. No, it's independent. So that doesn't make much sense to me. What I do want to know is, I think that we know FV is 28. So the force applied on the input winch is going to be FV over L total. Okay. Call that F in. Okay. And then the force times the radius of the input, which is D over 2. D in input torque is that amount. And then this still holds. That's just a motor characteristic. So let's try T in instead. 1.3. So it got less. Wait, what? Oh. Wait, because the D in changes. Huh? Of course, because as we're modulating the gear ratio to get a larger, to be able to have a larger input diameter, you know. So that's why this doesn't matter. Really interesting, because that's our constraint, is the amount of, you know, our operating point is our constraint, S equals 0.5. Wow, fun. Okay, so it means that we can go with whatever gear ratio we want. That's really what it means. But you do have to keep in mind that it will change the time, the opening time, directly if we increase the number of desired rotations at the input. So we could double this by saying we want the motor to rotate 2 times to open the valve instead of 1. So it's good to keep that to a minimum. Before I had it at 0.5. I think I'll have to go up to 1 because that gave us a better safety factor when we're using low voltage and a larger stroke of 2 millimeters instead of 0.88 millimeters. That's the methodology here. That's what we're changing. So yeah, the gear ratio can be whatever, like 8, for instance. That means that the input distance will be 16, right? 16 millimeters, right up here. And that can be accomplished with a 5 millimeter shaft. 5.1 millimeter shaft, because that's 16 divided by pi. Okay. Is that really 16 divided by pi? Of course it is. Of course it is. Just want to check that math still exists. Yeah. Okay, cool. 16 divided by pi. So 5 millimeter shaft or gear. This is all winch stuff, though. I don't know another way to do winch stuff. So what is 8? 8 is 2 times 2 times 2. 2 to the third. So if we have 3-stage transmission, where we have 2, mechanical advantage of 2, then a mechanical advantage of 2, then a mechanical advantage of 2, we need an input pull distance of 0.5. I mean, a winch seems to be like the most straightforward way to do this, but that has compliance unless I use a really stiff cable. I really don't like using winches in mechanisms. I really don't like it. But there's got to be another way. There's certainly another way, right? Like, come on. Come on, man. Rigid. Think rigid. Rigid mechanisms. Yeah, all we need to do, mechanical advantage of 8 in total. But we can do whatever it takes to get there. And I'm going to avoid winches like the plague. But that means I also want to try to figure out what I can do to have constant mechanical advantage without using winches, because the mechanism I have now also has a variable mechanical advantage, which is not great. A winch is this kind of mechanism. A cable or a rope wrapped around a spool, and you turn the spool to pull in the cable. Now, it's not as bad since I only need this to rotate once around. And I'm kind of like, well, I could use, instead of a rope, I could use a 3D printed thing to apply tension, but then that could wear down. Like, if worse comes to worse, I'll use a rope. That's fine. I'm okay with that. But I want to see what else we can do. Yeah. If we're just going for gears, this is still too much, man. Maybe it has to be a winch. Does it have to be? Gears would be nice. I'm gonna admit. Gears would be nice. So everything that fits over here, somehow transmitting power around the circumference of this bracelet, which we accomplished before with the levers, but now we can't use levers anymore because we want to do a full rotation. And also the levers have a variable transmission. I'm going to start drawing some shit. So I'm just going to pretend there's a point like here. Okay. And that point has to move 2 millimeters this way. That's consistent with the theory. Okay. Picturing yourself falling down the stairs at night. What do you mean? What does that have to do with Charlotte? That's horrible. I want to imagine that I have a lever somehow. Right? Not looking at the physical yet, just the mathematical. So these are equal. So this is about where this pivot point is going to be. And if that lever has a mechanical advantage of 2, that means this is all parallel and equal. Okay. So obviously, I wonder if I can make a driven dimension. Is that possible? Let's try that first. Then try this. Yes, create driven. Okay, and then what happens if we delete this? It's still driven. But also incorrect. What? Oh, no, it's not. It's always 4. Of course it is. Because it's 2 times 2. Great. Well, this is nice. It doesn't stick out too far. But I am kind of wondering. What can we get away with? That's a good idea. Yeah, that'll be a cool Charlotte project. I think that's great. I am printing some of your parts now. Oh, it's done. I should print the next one. Well, I gotta check how it looks first. But Yeah, should be good. Let me just get this ready. Ba, 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 ba. Battery config. Battery holders and next part. Okay. Great. No, 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 no. Go away. Slice now. All right. Okay. Be right back. Nice. That's right. 610 is a Pioneer customer. And also I would like to report that my 3D print settings were so good, I'm very excited. Oh, this is such a nice comment. J Films just commented on my short. This is so freaking cool. Been watching since before the PhD. Keep up the wonderful engineering work. I just know you are inspiring people to make the world a better place for the next generations. Thank you so much. That's very kind. Okay, so what are we doing? CAD. Right. So the thing is, whoa, 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 whoa. Did you guys see that? What was that? That was insane. So just because this travels 2 millimeters doesn't mean it needs to be attached to something that travels 2 millimeters. You know, it can just be pushed down on. And then the mechanical advantage isn't theoretically the same, but like might as well be. So what I'm thinking, because this is kind of sticking out here, I was kind of wondering if I could get away with something like a circle shaped lever, you know? So we put that there. Like the pivot point could be that far in, but where's our motor? Because we might need to go past it. Yeah, our motor's there. So if we can attach to the top and the bottom, that could work. let's just see. Are you changing the linkage reduction ratio at all? I'm changing it, but I have already figured out how I could change it. So we've basically changed a lot of the parameters. The input stroke is not the same because I found out that that we don't actually get a decent enough safety factor if our input stroke is 0.5 and we want a larger output stroke. So I'm changing the input stroke to be a full rotation of the motor. That's a key change, which means that we can really make the reduction as much as we want. But right now I'm going for 8. It could be less, but I just want to see what kinds of geometries we can generate that would be reasonable. So yeah. Go away, circle, go away. Okay. I'm gonna get I'm just like, can we get away with what I want to get away with here? Maybe. But the motor, we definitely can't do pretty much any geometry in this area because that's going to be the motor. So I'm thinking about where the linkage attachment point is going to be right now. What? Oh yeah, I want to see this again. What's that? Oh, that's the motor cap. What's this? Yeah, okay, cool. So if we put the pivot like over here, you know, you don't want it to be pushing down like too much. Let me get rid of these lines because they're not really serving me a purpose at the moment. They're kind of just clutter. So whatever kind of surface I'm going to have here, like that could be reasonable. And this here. Well, hold on a second. We know this is going to be coincident with this. Okay, and let's just say, okay, and let's say it also has a midpoint. Oh, my knee is killing me. Fuck, I'm gonna get some Advil. This is killing me. Jesus, I don't know why I have to be doing so many dangerous things. This is what I do. good stuff, man. Ugh. Okay. Oh. Excuse me. Okay. Midpoint constraint. So I'm thinking about the rotation point. You know, the fact that I still want this to coincide with this point here, and it's going to be the same length as this point, as this line, but it's not necessarily going to be at the midpoint. You know what I mean? It's going to depend on where the axis of rotation is. So how do I figure that out? That's a great question. Basically, it's a circle. Let's just draw construction circle and another construction circle, concentric because they have the same axis of rotation, and this line and this line are attached, this line and that line attached. Okay, so that's what it looks like pushing down on this point if the axis of rotation is here. Okay, so it's not too bad. As you can see over here, the angle is a little bit less extreme, right? But that's if the pivot is outside. I kind of want to have it inside. That's way too crazy. But also, I think this isn't the only constraint. Right? Because there's 2 degrees of freedom I'm moving here. Yeah. Interesting. So if I make this safely here by like, I don't know, what's safe? Maybe 3 millimeters. And this one safely in here by, I don't know, 5 millimeters. Where does that put our pivot? Oh my God. Yeah, it's kind of too far, I think. I think 3, no, I mean, to be really safe, well, 3 is okay. 3 is okay to be safe. That gives you 6. 3 and 3. How about that? All right. So this is telling me now that this is fully constrained. And this is not so bad. That is interesting. I guess it makes sense that the pivot point would constrain that. Yeah. So 2 degrees of freedom. That makes sense. Okay. So now we can deal with whatever else, which is tangent arc between here and here, and tangent arc between here and here, and maybe tangent over constrained. Oh Lord. Right, okay. So that's like pivot is there, some kind of arm geometry here, going to this flat point here, going here. And then you have to think about the other side of things. So this distance and this distance are a little bit different. But if we're going for 2 millimeter travel over here, we need to go for 4 millimeter travel somewhere else. That makes sense, right? And if I want to set that inset, this mechanism inside, that would be best. And if I want to make it look nice, then what happens? If I mirror this thing across this line to make it symmetrical. Interesting. Very, very interesting. And what if I do like this? You know? And that means similarly, because I just want to make sure that I'm understanding this correctly. Yeah, I mean, that's what I expected. Similarly, though, we have this thing, and we can mirror that line, and it should be the equivalent effect, but in a rotated frame. And here we get out just under, well, I think, is this 4.132? It's hard to tell. Basically depends on what we put in, but it's approximately there. It depends on how we're pushing on it, of course. It doesn't just depend on the geometry. It depends on where on this lever we're pushing at it. And if we do a distance of 2, of a distance of 4 to push on it, then yeah. Okay. This is not bad. But I am a little... Oh, what has happened here? Whoa, 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 whoa. Major problem. Major L. Huh? I'm sorry, sir. You are not my friend. Dude, what huh? Huh? That's all good. Give me another arc. Oh, Lord. Okay, because... $71.698. 71.698. Yeah, this is... Okay, so that's the shape. That's the shape. The mirror is doing a weird thing for some reason.
really weird thing. Let me try that again because I'm a little bit wigged out by that. Yeah, what's up with that? Oh, this isn't in the midpoint. That's the thing. I drew this at the wrong place. That's the midpoint. Duh. It's not about what you're pushing on, it's about the shape of this lever. Yeah. Okay. Cool. CAD Goblin back to his usual stuff, and today I'm blue. I'm blue. Okay. So that's a lever with the mechanical advantage of approximately 2, maybe, right? And that geometry could feasibly work where the pivot is hidden here and the application point is also going to be hidden. So nice, good start to having a hidden valve actuation mechanism. Very good start. Now we have to make this go 4 millimeters that way somehow. Push on this 4 millimeters and with our motor pull 16 millimeters, right? So we got rid of the 2. Now we have to do a 4. Wow, good night, Cream. Cream is on the other side of the earth, everybody. Thank you, Cream, for tuning in. I can't believe you were the villain in Supergirl. I can't believe you did that to all those women. Oh my goodness, so sad. Anyway, good night. I'm just kidding. Push on this 4, pull 16. Push on this 4, pull 16. Crazy thing is, I know we can't just use gears. Like, I feel like I know that we can't because, like, the angle here, which I'm going to make as a driven dimension, where's that angle? 5.4 degrees. That times 8. That times 8 is not 360. So we kind of have to use winches or something to translate linear to rotary motion. We can't just use rotary motion, even though I really, really, really want to. I was not gonna watch Supergirl, but now I need to. Yeah, you're the villain, dude. You're Cream. I have been using this alias for years now. All right, that's what I'm talking about. Well, let's look at villain from Supergirl. Creme. They call him Cream. Creme of the Yellow Hills. Is he a comic book character? It's your boy, Cream. Well, I guess that he looks different in the comic books.
That's your boy Cream. He looks better here, for sure. Cool. Cool, cool, cool. Back to this. Totally not me. You don't have 11,000 face piercings? That's a shame. I really don't want to use pulleys and stuff like that. I really don't want to. We could take the multiple lever approach again. Except the part where we absolutely can't. Because then I'd have to gear like a full rotation of this motor to something that only does a half rotation. Like I could do a 2-to-1 gear ratio here, maybe. And then I would be left with a 2-to-1 here. I need a 2-to-1 gear ratio. And then something that transfers 8 millimeters to 4 millimeters. That simple. But 8 millimeters is tricky. We don't really, do we have 8 millimeters to even work with here? We have 11.5. That leaves us 1.5 about on either side of the mechanism housing. So that could work. But again, the linear to rotary component is just tweaking me out. Oh, God. I could have another lever. I could do exactly that. I could have another lever and then a gear to lever thing. It would have to be like a weird conjugate gear shape though, because this is here. Let's leave that sketch there. This would be a really interesting drive gear shape. But it might not be crazy. Like, it might not be as crazy because the axes won't have to be like totally skew. The thing that sucks about like bevel gears is that they typically don't make them, like, I don't know how to get, like, it should be pretty easy, right? To figure out bevel gears. Like, if I want one gear, like, on that axis. Not this axis, but no, this axis. Exactly, this axis. And then one on this axis. Like, that's not skew, it's a simple angle. Like, they could have their mating surface literally right here. Halfway in between the two. So let's do that. Let's trim here. Some deja vu right now. Yeah. Okay. Parallel. Okay. Please let me select some lines. I'm going to save this before it disappears forever. I want this and this and this to be equal. And then I just want to make sure that we're representing equal angles. Except that only works if they're the same gear size, so that won't work. Equal. We're actually looking at something that's much bigger. I wonder if that's how it works. Like, if I'm designing like a bevel gear system and I'm like, here's two lines, they're X and they're X, they are parallel, they are also equal, bing, bing, and then this one's also equal to this one. Like, I could have gears like that. I think that's typically how that goes. I think that's how that goes, right? Because then, what if I, yeah, if I'm doing like, I don't know, point and point. if I'm doing a shape for a bevel gear, like mock bevel gear type thing, like this. So if that's my one bevel gear, that's my other bevel gear. Shape there. Okay. You see those two trapezoids there? Question I have is, how does this end up contact-wise? That is 7.637. 14.824. That's double, right? You're not impressing my stream. Everybody knows you're using a calc. I forget what the numbers were. Show me the numbers, Mason. $7.637, 14.824. Is this right? Yeah. So it's not quite double. Even though this angle is double this angle. Oh, because they're not. These are the rotations. Those are the rotations. Oh. So what if I take away the... I kind of have an idea about how to make bevel gears now. I've never actually thought about this too hard. I've always tried to find 3D models of them. But I want to see if I take this away and I say I want this to be twice as much as this. So basically saying that this, well, let's go here to here, and this are parallel, and this equals that. What happens? This is a true bevel gear situation. Yeah. I can do with this whatever I want. Depending on how close to the axis I want it to be. Okay, that's pretty cool. So these could be real bevel gears. Huh? But of course, we have a constraint on this distance here, because that's not going to cut it. That's going to come way out. This has to be only like, okay, this is where it all falls apart. This is where it all falls apart. This cannot be very big. This has to be like 4 millimeters. Okay. So that's so that's where this all falls apart. Because this is just not this is just not happening. Wow, seriously, dude? What the? Okay, what if I make it more? 5 millimeters. Still sucks. 6 millimeters. Still ass. 7 millimeters. Okay. Not great. 8 millimeters. This is why gears suck. Because they need to complete a full rotation. Unless I don't need to complete a full rotation. But I'm pretty sure I'm going to need a full rotation. One way or the other. This is why levers are boss, because they don't need to rotate all the way around. With here, I'm planning on making these small enough such that they don't like poke out when I revolve them all the way around, but it's just not possible. It's just not possible with the speeds that I have. Because this is the absolute max, for sure. You can't do any more than 8 in diameter. Like, this could maybe work. The geometry is not like cooked. If I measure from here to here, it's 1 millimeter, but still. At what point do I just say that a cable-driven mechanism is actually easier? You know? Yeah, I don't think the bevel gears are gonna work. I'm glad I mapped them out before looking for ways to make them, because it's just too big and too small at the same time. Ugh. Okay. 5 millimeter capstan shaft is potentially the input. 5.1 millimeters. With a 3 millimeter shaft, that only gives us 1 millimeter wall thickness. Not the best. But it could be done. Boy, oh boy. Well, friends, I think that this is going to require some thought. So what I'm going to do is log off, work on some other stuff, and think about it. This is done. Been done for a minute, I think. Cool. Cool. Well, thank you guys for coming, and I'm going to eat some lunch and try to enjoy what limited mobility I have. And thank you guys for tuning in. I hope you're all staying safe during the smoky times. If you're in the smoky times like I am, if you're American in the North, East, Midwest type area, thank you guys for coming. And I'll see you guys next time. Bye-bye. Thanks for stopping in.